Hello. Today we are going to have a slightly more mathematical lecture where we're going to dive into some really important concepts related to model building, the concepts of bias and variance and how they play a role in the kinds of models that we will be constructing in this class. For that we're going to begin with a quick recap of some concepts around random variables that we introduced at the beginning of the course. Those should be in your mind, but I'm going to take a few minutes to refresh them for you because they're important to set the stage for today's lecture. So first, let's recall the definition of a random variable. The term random variable gives a lot of people, myself included actually, because I wasn't trained as a statistician, sometimes a bit of a hard time because we think of it as the word variable is the first thing that jumps to mind, but it's important to remember that a random variable is a function. It is a numerical function from a sample space where we sample at random according to a probability distribution, and we produce real values. So it is a real valued function from a sample space. Another name for a random variable is for a numerical function of a sample is a statistic. We saw this terminology introduced in data 8. We call it random because the sample from which the function is drawn is drawn at random according to the underlying probability distribution, and it is a variable because the value depends on how the sample actually came out, and so when you see the term random variable, in your mind you should be thinking real valued function, but a real value function that has a probability distribution associated with it. Notationally, we tend to use uppercase letters, later the alphabet X, Y, Z, etc. So the most basic property of a random variable, and the one that we use the most fundamental one, is the expectation of the random variable, which is the weighted average of the values that X can take, but weighted precisely by this probability distribution that is associated with a random variable. So this is how we define the expectation of X. It is the sum of the values X can take. So lowercase x are the values that the uppercase X can take. So it is the sum of all the possible weights it can take, each value weighed by the probability of that value being, of X taking that particular value. And this is the case for a discrete probability distribution. And if we have a continuous one, this sum becomes an integral, and there's some extra technical details that we won't concern ourselves with in this class. So this is a per value definition, and we can also write the same quantity if we think of sampling. And so where S is now a sample that includes multiple possible values, but the same idea applies. And a fundamental property that comes from the definition of random variable and the definition we just saw of expectation is that expectation is a linear operation. So in its more concise and general form, the linearity of expectation is expressed in this equation that says that the expectation of a linear combination of two random variables, meaning a sum that has constant coefficients a and b. A and b are real numbers. They're not random variables, they're just numbers. And x and y are both random variables. The expectation of ax plus by is a times the expectation of x plus b times the expectation of y. So the expectation is a linear operation, so it distributes over sums and constants come out. This is the general property of linearity, and we're going to use this a lot. It's an absolutely fundamental property, and this should be always in the back of your minds. So in summary, this is a quick recap basically of lecture 3 in 2 minutes. Random variables are functions of our sample, and the expectation of a random variable is the weighted average of all of its possible values weighted by those probabilities. Expectations are linear transformations. So the expectation itself is a linear operator. With that refreshed, we're going to dive into the second key concept in a random variable that comes after expectation, which is new in this course. I mean, you have already seen some of these ideas in data 8, but we had been holding off on this key concept up until now, until it was really most pertinent, and it is the concept of variance and covariance. So now that we've refreshed in our minds what expectation is, we introduce the concept of variance. And what is the variance of a variable? Variance is a way of getting a sense for how spread out a variable is. And we define that by computing the expected square deviation from the expectation. So This is a mouthful, but we're going to spend some time kind of dissecting this definition a little bit. So this is the definition of variance. We take the expected value of the deviation of x from its expected value. So x has an expectation e of x, and we ask, what is the difference in general between x and its expected value? But because we want to measure, remember how we looked when we built loss functions, we built our errors in the L2 loss as squares and not simply as y minus the predicted value, but rather that quantity squared. Well, the same idea applies here. We are not interested in taking into account the sign of these deviations, but rather their value only. And we want to treat positive and negative deviations from the expectation equally, so we square them, and we take the expectation of that quantity. So because of this construction, because we're measuring units of x but then taking squares, the units of the variance, or the squares of the units of x, whatever the units of x are. So if we are interested in a measurement of this spread in the same units as x, which is often useful because sometimes we want to say this is this distance away in units of the quantity from a value, then we can take the square root of this quantity. And that's what gives us the standard deviation. So the standard deviation is nothing but the square root of the variance, right? The square root of this quantity. And by construction, and this is really, really important, by construction, these quantities are both non-negative, right? Because we're taking the expectation of a square, right? Remember, the expectation is a sum, only weighted by probabilities, which are positive numbers. So if we're taking the sum of numbers which are squared and with weights that are themselves always non-negative, then this quantity can never be less than 0 ever. So this quantity by construction is always non-negative, and this will come back into play, and it's a fundamental property that should be in the back of your head. So we use the concept of variance to try to quantify chance error, basically. How far away from its expectation can it be just by chance? Where by chance we mean very specifically according to the probability distribution that defines x, right? That is what we mean by chance, right? When we use the word chance or at random in this context, we always mean if we draw from its probability distribution. Now, there is an important refresher and connection to data 8 that comes into play here, which is something that you already saw under the name of the Chebyshev's inequality. And Chebyshev's inequality is a very genetic property. It's one of the most fundamental properties of random variables, and it applies to random variables that belong to a pretty broad class of distributions. All they have to have is an expectation and a variance that are defined at all. They must exist, and as long as the probability distribution of x has an expectation that is finite and has a variance that is finite, that are defined, then we can say that in general most of the probability is around the expectation, plus or minus a few standard deviations. And there's in data 8, there's a lengthier discussion of this, and it gives a lot more detail. But the key idea here is that for pretty much any probability distribution that you will encounter in this course, you can assume that most of the mass, if you will, is concentrated around the expected value, give or take a couple of standard deviations. So you can't expect in general to have, you will not find in general a random variable that has a defined expectation and variance, but where somehow the expected values are here, and it has a variance that is, let's say, like this, but somehow there's a huge amount of probability over here. That simply cannot happen. Chebyshev's inequality is one of the first inequalities that belongs to a class called concentration inequalities, that are basically theorems that describe how does probability concentrate around expectation values, and it's a very important result. Mathematically, if we define the expectation of x as by mu and the standard deviation of x by sigma, then the mathematical statement of Chebyshev's inequality is given here. It states that the probability that x in absolute value, so that x is away from the mean by more than k standard deviations goes down like 1 over k squared. So if you look at being, say, square root of 2, for example, if you ask if I'm plus or minus square root of 2 standard deviations, so square root of 2 is about 1.4, so 1.4 standard deviations to the right or the left of my expectation, then the probability of being further away from that is less than 1 over square root of 2 squared, which is a half. So that tells you that for any non-pathological probability distribution, the probability of being more than 1.4 standard deviations away is less than a half. So at least a half, 50% of the probability is concentrated within 1.4 standard deviations, 1.41, whatever, give or take. So this is the basic idea of Chebyshev's inequality. We won't be using it extensively in this course, but it's a piece of intuition that you should keep in your mind when you think about what is realistic or possible with probability distributions and random variables or not. Now, in computations, there's a different way of writing the variance that comes in very handy, and we're going to derive this little formula right here for just a moment. We're going to derive it here by constructing, you have the derivation in front of you in the slides, but it's always nice to see these things kind of done by hand. So what is the definition of the variance? It is the expectation of, and I will be using interchangeably expectation with square brackets and parentheses just to make the notation sort of more convenient. So as a reminder, what is the variance? It is the expectation of the square of the deviation of x from its value, right? That is the definition that we gave in words, and this is spelled out here. And if we want to reorganize this equation, we can expand out the term in the parentheses. So this is x squared minus 2 times x expectation of x plus expectation of x quantity squared. Right? Now let's keep in mind what we said about the linearity of expectation, right? So now because this is a sum of 3 terms, right? There's one term here, one term here, and one term here. So the expectation distributes over those 3. So I can write this as expectation of x squared minus twice expectation of x expectation of x plus expectation of x squared, right? And I've already made use of the fact that the 2 right here, that the 2 was a constant, and I pulled it out of the linear term of the expectation already. But there's a few more things that are constants. Expectation of x is itself a constant, right? The expectation of x right here is a constant, and the expectation of x quantity squared is also the square of the expectation of x is also a constant. These are just numbers. So these things also come out of the expectation easily. So what we're left with is the following. This is the expectation of x squared minus twice expectation of x times expectation of what's left in here, which was this x, right? Plus the expectation of x quantity, quantity squared. So now you'll notice that this right here and this right here is the same thing, because it is the expectation of x, all of that squared, right? So we have expectation of x squared minus twice expectation of x squared, which gives us the final expression we were after, which is that variance of x is equal to the expectation of x squared minus, because we have 1 positive, 2 negatives, minus the expectation of x itself squared. And this is the final expression that we were looking for. So this derivation is summarized right here, but I think for these kinds of things it's nice to do it by hand. You should convince yourself that that all of this little bit of algebra, these quick 3-4 lines of algebra make sense to you and that you find them intuitive and clear. So with this alternate expression, it's often more convenient to do certain computations. For example, let's say we want to find what is the variance of a roll of a die. Remember, a 6-sided die has an expectation of 3.5, right? It's the mean of those 6 numbers. And if we use this formula, computing the variance of the random variable x that describes the roll of a die is quick work. It's the expectation of x squared, so it's the sum of the squares divided by 6 minus the mean squared, 3.5 squared. That's about 2.9, give or take. And when we look at this expression, something jumps out more clearly than something which is sort of implicit or a little bit more hidden in the original definition, which is that if x is a centered variable, meaning it has 0 expectation, then the variance is just the expectation of x squared. So this can be a handy thing to keep in mind when you know that your random variable has 0 mean, which is often the case, especially after you do something called standardizing it. Though in that case, we also know what the answer is for the variance. But if you haven't fully standardized, but simply remove the mean, which is common in a lot of data analysis processes, it's called centering your variables, then the variance is immediately computable as the expectation of x squared. And also, because, as we said, the variance is by construction and on negative quantity, it means that here we have an inequality, that this is greater than or equal to 0, which means this has to be greater than that. So by definition, this has to be by construction. The expectation of x squared has to be at least greater than or equal to the expectation of x squared. And in fact, this inequality turns into an equality only when x is a constant. And obviously you can use this formula and turn it around. If you know the variance and the mean of your random variable, then the expectation of its squared is equal to the sum of these two terms, right? You move this term right over here to the left of the expression, and so it gives us a quick way of computing the expectation of x squared. Now, what happens in terms of linear transformations with the variance, right? We already know that expectation itself is linear, but what happens if we take a random variable, x, and apply a linear transformation to it, right? In this case, a simple one where we multiply it by a and add and shift it by b. It turns out that just to shift by b by itself, if a was equal to 1, the expectation of x plus b, the variance of x plus b doesn't change, because if the blue histogram is the original distribution of the random variable x. Shift by b units, in this case by about 4 units, just gives us the same distribution at a different location, but it's equally spread. However, scaling by a does affect the spread. If we multiply each value, then those values, the actual data will spread out. This is what that histogram would look like, and we will see that next mathematically. We're not gonna do this algebra in detail. You should convince yourself that this algebra makes sense to you. But a couple of lines of similar algebra to what we just did, using the properties of linearity, of expectation that you've seen already, and the notion that a and b are constants, right, and that the expectation of x is itself a number, so that it comes out of expectations, give us this result. But the variance of a linear transformation of a random variable is unaffected by the constant term, but the constant comes out squared, right? And this is basically implicit in the fact that the expectation is defined through squaring. Is a construction that involves x squared and not x. So the a that accompanies the x comes out squared. Intuitively, that's how you can think of it. And the standard deviation comes out to be scaled by the absolute value of a, and that's important because it's possible that a was negative in the first place. But you should be careful to keep this absolute value in mind. You don't get a negative standard deviation after you linearly transform a variable, even if the transformation involves a negative coefficient. That coefficient still comes out positive out of the standard deviation, right? So standard deviation is always a non-negative number by construction. And finally, in this section, we'll take a quick look at the concept that we already discussed in Data 8, but let's refresh it, which is the concept of standardizing random variables. So if I have a random variable x that has a known expectation and standard deviation, or variance, right, we can define a linearly transformed version of x that has roughly the same kind of structure, but whose units are very special. If we take x and subtract the mean, and divide that by the standard deviation, we get x in what's called standard units. And a couple of quick steps of algebra, or you can just do it in your head pretty quickly. Imagine computing what is the expectation of this quantity. Well, it's going to be the expectation of this minus the expectation of that, which is the same thing, 0, right? And what is the standard deviation of it? It's going to be the standard deviation of this, right? And this is going to come out in absolute value. It was already positive. You're dividing the same thing. You get a 1. So, in summary, the units of x in standard units are such that x in standard units is always going to have 0 mean and standard deviation 1 and variance 1 as well, right? Because in this case, the square root of 1, the square of 1 is also 1. So standard units are a very convenient way of representing a random variable in where everything is 0-centered with 1, if you will, right? And so if you want to make comparisons of things that are, for example, measured in different physical quantities, right? But you want to compare their statistical distribution and properties, then standardizing them is a very useful thing. To do, because it could be that the physical units for reasons that are independent from the statistical properties of these variables are very different in values, and so it would be difficult to make numerical comparisons between quantities that are very different in size. This brings them all into this sort of 0-1 little box where you're only looking at the statistical distribution of the variable rather than artifacts from the definition of the units.